Hello, everybody. This is Bert Dixon. I'm here to present a lesson on using summation notation, which is also known as sigma notation, because we use the Greek letter sigma, which looks like this. This is the Greek letter sigma, and it's the equivalent of our letter S in our alphabet. So that is, we use the letter sigma because of the S, S standing for sum. So it looks kind of like an E, but it's really not an E. Think of it as an S for sum. And so it's what we do when we want to express a sum that has multiple terms that can be calculated algebraically. So the way we expand a sum using sigma notation, this variable is called the index. And you can use any letter you want. I'll use a variety of letters in today's lesson. It doesn't really matter what letter you use. That's the index, and that this bottom number tells you where to start. That's the number we're going to plug into this expression. So that's the first number we're going to plug in to start with, and this is the end. That tells us where to stop. And so when we plug in I equals 3, that's our starting letter. Our expression is 2 times 3 plus 1, so that would be 7. And it is a sum, remember S for sum, so we're adding in between each term. And so then when we plug in I equals 4, we get 2 times 4 is 8, plus 1 is 9. And then next we'll plug in I equals 5. And when we plug in 5, we get 2 times 5 plus 1, so that's 11. And we keep going until we plug in our final number. So now we're still going to plug in I equals 6, and then I equals 7, and that's where we'll stop because it says to end at I equals 7. So we're plugging in the I values from 3 to 7. 3, 4, 5, 6, and 7 are the I values that we're plugging in. When we plug in 6, we get 13. And when we plug in 7, we get 15. So that is the expanded sum. And then if you wanted to add those up, you could just do 7 plus 9 plus 11 plus 13 plus 15, and that adds up to 55. So this is called the expanded sum. And then this is the value of that sum. Now go ahead and give problem B a try. Pause your video, expand the sum, and then add up the terms to get your final value. Press play when you're ready to check your solution. Okay, so we're going to start with this one with m equals 5. I realize I have a typo here. This should be an m. And so now we have, if we plug in m equals 5, that's going to be 15 minus 2 is 13. When we plug in, so this was m equals 5, then when we plug in m equals 6, we're going to have 18 minus 2 is 16. Then when we plug in m equals 7, we get 19, 19, because it's 21 minus 2. And then when we plug in m equals 8, we get 22. And then when we plug in m equals 9, we get 27 minus 2 is 25. And you'll see that these are just going up by 3 each time. Plus 3, plus 3, plus 3, plus 3. That's why. And so now the next one is going to be m equals 10, and we get 28. And that's our last one. That tells us where to stop at m equals 10. And so now if you add those up, 13 plus 16 plus 19 plus 22 plus 25 plus 28, you get 123. Okay, now go ahead and pause your video and try this one. Okay, when you plug in 2, we're starting with j equals 2, so that's the first number we're going to plug in. When we plug in j equals 2, we get 2 squared plus 1, so that's 5. When we plug in 3, 3 squared plus 1 is 10. When we plug in 4, we get 16 plus 1. When we plug in 5, we get 25 plus 1. When we plug in 6, we get 36 plus 1. When we plug in 7, we get 49 plus 1. When we plug in 8, we get 64 plus 1. So that's our expanded sum, and that sum is equal to 5 plus 10 plus 17 plus 26 plus 37 plus 50 plus 65. That's equal to 210. You can also check answers or sums that have maybe a larger index. For example, if let's say I had the sum, same sum, j equals 2, but we go to 100 this time. That would be a lot of terms to write out. And so if we had a larger value, we could use our calculator for something like that. If you press math and then go down to the very bottom, I'm going to use up arrow to get there faster. There is summation, and then we can enter, you can use any letter you want. It's easier to use X because there's an X button right up here, the one that's red now on my keyboard. So I'm going to use X instead of J just because it's easier to type in. So it's 2, we're going to go to 100, and then we'll type in X squared plus 1 is our expression, and then press enter. And it gives us our final answer, 338448. Okay, so again, that was by using math. If you go up arrow, it jumps to the bottom of the list, and we could go to summation. Okay, the next part of our lesson is to go the other direction and take an expanded sum and write it using summation notation or sigma notation. Those words are synonymous. Summation notation or sigma notation, they mean the same thing. So in this one, by the way, there are infinitely many ways of doing these depending on what we start for our index. And so one way that we could do this is realize, okay, it's going up by 2 each time. So it's a linear expression. And so what we found in the previous problems, like in problem 1, when there was a 2 here, these went up by 2 each time. When there was a 3 here, they went up by 3 each time. So for this problem, they're going up by 2 each time. So we know it's going to be an expression like 2i plus or minus something. So if I want to start at I equals 1, by the way, you can start at any I value you want, but if I start at I equals 1, I'm going to have 2 times 1, which is 2. I would need to add 3 to get to 5. So when I plug in 1, that's going to be 2 times 1 plus 3, and that gives me 5 as my answer. Okay, now when I plug in 2, I get 4 plus 3, which is 7, and that matches. When I plug in 3, I get 6 plus 3, which is 9. So it seems like this expression is going to work. And to get 21 at the end, when is 2i plus 3 equal to 21? That's when 2i equals 18, or when I equals 9. So we know we're going to have to stop at I equals 9. 1 to 9, or you can count the terms. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. So if we start with 1, we get 9 terms when we count from 1 to 9. So that is one way to do this sum. Another way, you can start at any I value you want. So if I wanted to start at, let's say, I equals 3, we know it's going to be 2i. That would give me 6, so I'd have to subtract 1 to get 5. So we could say I starts at 3. 2 times 3 is 6, minus 1 gives me 5. That matches the first number. Now when I plug in I equals 4, that's 8 minus 1 is 7, and so on and so on. Now our ending value is going to be different, because when is 2i minus 1 equal to 21? That's when 2i equals 22, or I equals 11. So this number is going to have to be 11. If you count from 3 to 11, that is 9 terms. So there's another way to write it. So since we can start at any I value that we want, it's typical to try to write it starting with I equals 1, but that's not required. So since we can start with any I value we want, there are really infinitely many answers, infinitely many correct answers for this problem. Okay, so there's 2 possible answers. All right, go ahead and pause your video and try part B. Press play when you're ready to see the solution. Okay, in this one we see another linear expression, because this goes up by 3, up by 3, up by 3, up by 3. So we know it's going to be a linear expression with a slope of 3. And so we can say 3n, I'm going to start with n equals some number. I like to start with 1, so we'll try to make it work there. So 3n would give me 3, and then I need to subtract 2 to get an answer of 1. Now let's test it and see if it works when n equals 2. That would be 6 minus 2, which is 4. That works. When I plug in 3, I get 9 minus 2, that's 7, and so on. And so now we just need to figure out where should we end. When does the expression 3n minus 2 produce an answer of 43? 3n equals 45, so n would be 15. So if I count from 1 to 15, that will end at 43. Notice if I plug in 14, 3 times 14 is 42, minus 2 gives me 40. And then when I plug in 15, I get 15 times 3 is 45, minus 2 gives me 43. So this sum appears to work. Okay, in the next example, we see that it's not a linear expression because the difference from term to term is not consistent. A couple things we should notice, though, is that the signs are alternating. It goes minus, plus, and so on. So we're going to have to account for that. And then to produce these numbers, you want to look at the numbers 1, 8, 27, 64. What kind of numbers are those? What we want to recognize is this is 1 cubed, this is 2 cubed, 3 cubed, 4 cubed, and then 11 or 1331, the cube root of 1331 is 11. This is 11 cubed. Okay, so by recognizing that, we can say this is the sum of p cubed, where p starts with 1 because that's the first number that we're cubing, and ends at 11 because that's the last number that we're cubing. Okay, so that would produce these numbers: 1 plus 8 plus 3 cubed is 27, plus 4 cubed is 64, and so on to 1331. The problem is it doesn't have the alternating signs. So let's see what happens if I put in a -1 to the p power. When p is 1, I would get -1, so that would be negative. And then when p is 2, it would become positive. And then when p is 3, it would become negative, because anytime it's raised to an odd power, we're going to get a negative result. And so this now alternates in sign, but the problem is the signs are backwards. We want 1 to be positive and 8 to be negative. So what I can do then is change this, instead of p, make it p plus 1 or p minus 1, because now when p is odd, we add 1 to it, and that makes it even. So now when I plug in 1, I get -1 squared, which is +1. but when I plug in p equals 2, I get -1 cubed, which is going to be -1. And so then that now produces the correct signs. And 11 plus 1 is 12, so -1 to the 12th power is going to be positive. So now we have the correct summation for that one. Okay, for our last one, part D, go ahead and pause your video, give that one a try, see if you can write it in sigma notation. Press play when you're ready to check your solution. Okay, so we want to recognize a pattern, and anytime we see counting numbers, 2, 3, 4, 5, that should make it easy to put in sigma notation, because we can say on the top, it's just, if we started with, let's say, n equals 2, then the number on the top is just n. So this is when n equals 2. This is when n equals 3, n equals 4, and so on. So the number on the top, we're just calling that n, and it's going to end when n equals 25. Now, how does the number on the bottom of the fraction compare to that? Notice that it's always 3 bigger. So 5 is 2 plus 3, 6 is 3 plus 3, 7 is 4 plus 3. So this is always 3 larger than whatever number we put on top. And so then that is it. If you wanted it to start with 1, then we could do this. On the top, to make a 1 into a 2, we would have n plus 1. And then the number on the bottom needs to be 3 units larger than that, so that would be n plus 4. And we would have to end at 24 then, because 24 plus 1 would give us the 25 on the top, and this 26 isn't going to work. This should be 28 on the bottom. That was a typo there. That's going to have to be 28 to fit that pattern. And then when n is 24, we get 24 plus 4 is 28. All right, that's it for today's lesson. Everyone have a great day.